and welcome to the 29th class in our course, the physics of materials. In the last class we looked at the diffraction process as it occurs in real space and the kind of description we would use for that, and as it would occur in reciprocal space and the kind of description we would use for that. As I mentioned, on the whole there is a material and there is a interaction of that material or the atoms in that material with the incoming electromagnetic radiation or with electromagnetic radiation in general. So that interaction is whatever it is. So the description that we use, whether it is real space or reciprocal space, is simply something that is for our convenience. We are creating these spaces and examining the interaction within the framework of that space, okay. And the reason we do that is for certain types of analysis, one description of the interaction works out more convenient than the other. So that is simply what it is. So there is no greater purpose to the analysis in that sense. So but at the same time we have to understand these approaches, because in the subsequent classes we will use those approaches to further analyze the impact of the interaction of electromagnetic radiation or of waves, electron waves, with the periodic structure of the material. And that interaction we will look at in the reciprocal lattice notation, because that gives us some insights which are very useful to us, okay. So it is in that context that we have looked at this interaction. Now where we finished off last class is basically we said we looked at the interaction in the reciprocal lattice notation, and we specifically found that if you have a unit vector in the incident beam direction given by S naught, and 1 by lambda is the magnitude of the wavelength in reciprocal space notation, and S bar S is the unit vector in the diffracted beam direction, or in the direction where we are looking to see if there is a diffracted beam, and again 1 by lambda is the reciprocal of the wavelength, and therefore the magnitude of the wave in the reciprocal space notation. Then we find that S by lambda minus S naught by lambda works out to H B1 plus K B2 plus L B3 in the reciprocal space. That is simply based on the notation of reciprocal space. More particularly, diffraction occurs when H, K and L are integers, and therefore this vector here, the difference between these two vectors and the resulting vector due to the difference between these two vectors has to be a valid reciprocal lattice vector. In other words, this should be a valid HHKL, okay. So when this happens to be a valid HHKL, we have diffraction, alright. So this is the condition that we arrived at the end of last class, and it told us how we would describe diffraction in reciprocal space. More specifically we will see, let us make a plot of this information, and that will further convey to us the important idea that it is conveying to us, okay. So the way that is done is we draw the reciprocal lattice. So some point we take as the origin of reciprocal space, okay. So this is arbitrarily designated as the origin of reciprocal space. We take the incident beam vector, okay. So that is the incident beam vector, and we draw it such that it comes and contacts this reciprocal lattice origin. So I will call this O, and this vector here is this S naught by lambda, and we make it contact this origin of the reciprocal lattice space. Now the reciprocal lattice is a series of points, right. So we will draw those points in just a moment. What we are going to say is, now we can actually in this diagram what we will simply do is we will draw a circle with this as the center, not the origin, but the end, the starting point of your incident beam as the center. I will just call it A. With A as center, I will draw a circle of radius S naught by lambda, alright. So approximately I am drawing it here. Okay, so this is a circle with S naught by lambda as the radius, and A as the origin, as the center of that circle. O is the origin of the reciprocal space. Now supposing I draw a vector like that, alright. What is this vector? The magnitude of the vector is the same as the magnitude of this vector, right. So there is no difference in the magnitude because it is a radius, it is a circle of the same radius, so the magnitude is the same. So the magnitude of this vector is 1 by lambda, alright. And so if I am, and this has a particular direction, so supposing I want to look for whether or not diffraction is occurring at this direction, in this direction, given that the incident beam is in this direction and its wavelength is lambda, what I need to do is first I will designate this as S by lambda, right, simply because first of all this is 1 by lambda, that is very clear because it is the same dimension as this vector here, and this is the direction in which I wish to see whether or not diffraction is occurring. So I will simply call this the probable diffraction direction S by lambda. So now if you look at the left hand side here, we have S by lambda minus S naught by lambda, that is a vectorial subtraction, right. This is S by lambda, this is S naught by lambda. If this is S naught by lambda, if you invert this, if you change, if you go the exact opposite direction, that is minus S naught by lambda. So S by lambda minus S naught by lambda means this vector would simply be inverted this way. So you are actually starting from this point, going to A, starting from O, going to A, and then going to B, let us just call this B. So therefore S by lambda minus S naught by lambda, which is the left hand side of this equation, is simply this vector which connects the origin O to this point B. Okay. So the left hand side is now this vector OB, the left hand side of this equation is this vector OB in this diagram. Everything is consistent with respect to, I mean we have just used a very consistent procedure, we have arrived at this. Okay. So S naught by lambda is here, S by lambda is there, and therefore OB is the left hand side of this equation. We are saying that this set of conditions of this incident beam direction with this wavelength and this diffracted beam direction with the same wavelength, this set of conditions will result in diffraction if the difference S by lambda minus S naught by lambda is equal to a valid reciprocal lattice vector. So that difference is now this vector here OB, OB is that vector. Therefore we are basically saying diffraction occurs when OB equals HHKL. Okay. So in other words this has to be a HHKL vector, alright. What does that mean? That means there is a valid reciprocal lattice point here at this point. Okay. Now I want you to think again for a moment this particular terminology that I am using, a valid reciprocal lattice point, and I will use this diagram to illustrate what I mean, alright. There is a difference between simply saying reciprocal space and saying a valid reciprocal lattice point. So in other words, in reciprocal lattice, reciprocal space, we have the following unit vectors B1, B2 and B3. These are the valid unit reciprocal lattice vectors, unit vectors in reciprocal space, valid unit. So if I start here, if I go, if this is the origin, and if I go, if this, let us say this is the positive x direction, if I go B1 I will get a point here. Okay, if I travel B1 I get a point here, if I travel again B1 here, 2B1 I get a point here, 3B1 I may get a point here, 4B1 I might get a point here, 5B1 and maybe this is 6B1. Okay. Similarly if we say this is the x direction and let us say this is the y direction, so this is x direction, this is y direction and z direction is perpendicular to the board. Okay. So if I go B2 in this direction I will get a point here, some we do not know what the values of B1 and B2 and B3 are, they need not be the same. So let me just arbitrarily say B2 is little larger, so I will say this is B2 value and this is another B2 value. Okay. So something like that and we continue this process. Okay. So just for convenience sake, I will just say that okay, for convenience sake we will just say that this coincided with the origin, let us not worry about it, simply because we will get a point there for the purpose of this diagram. Okay. So I have actually made a series of points here, they correspond to B1 and B2, B1 along the x direction, B2 along the y direction. Okay, so this is a set of points. Similarly, if I know the value of B3, I can continue to make the diagram below also, below this plane here. So we can put in a couple of points just for sake of completeness. And it would be very similar, the diagrams would be very similar. Okay, so so like this we would have a set of points, let us not worry about it, about the exact points, but it gives us the basic idea because this is just a hand drawn picture. Okay, so we have a set of points coming down this way and they are B1 and B2 in the respective direction. If you you can even plot it this way, and then you can also plot in the z direction information. If you had a software which would allow you to plot the z direction information, you can get it in this direction. So that is the complete information of this reciprocal lattice, that is in fact the reciprocal lattice, right. That is a lattice is a set of points, right. So these are all points, specific points, and that is then the reciprocal lattice, fine. Any region in between these points is in fact a region in reciprocal space, alright, but there is no valid reciprocal point in all of those locations, fine. So therefore there is no reciprocal point here, for example, there is no reciprocal point here, reciprocal lattice point, but it is a region in reciprocal space, fine. This is a region in reciprocal space that also has a valid reciprocal lattice point, that is the difference. So wherever you actually end up as a sum of B1 or B2 and B3, B1, B2, B3, some valid sum of those three, integer sum of those three will get you to one of these points, they are valid reciprocal lattice points. Anywhere in the middle it will not be an integer sum of B1, B2 and B3, it will be some fractional sum of B1, B2, B3, that will get you to some in between locations where there is no valid reciprocal lattice point, but it is still reciprocal space, fine. So this circle that we have drawn is a circle drawn in reciprocal space, okay. So it is in general it is in reciprocal space. At particular locations it is also touching valid reciprocal lattice points. In this case, for example, by symmetry somewhere down here there will be a point, if you actually draw it correctly, somewhere down there is a point where it will touch the reciprocal lattice point. So this circle is independently existing in reciprocal space, and at particular locations it happens to touch valid reciprocal lattice points, okay. And therefore those particular locations you will have you can now define that wave vector s by lambda as so at that point you not only have the correct magnitude of wavelength, which is 1 by lambda, but you are also having a direction such that this difference between the incident beam vector and the diffracted beam vector is a valid reciprocal lattice vector. Any valid reciprocal lattice point, if you connect it to the origin, if you connect the origin to a valid reciprocal lattice point, you have a valid reciprocal lattice vector which is designated by HHKR, it is a valid reciprocal lattice vector. Anytime the circle also touches that point, then it turns out that the difference, that circle is being defined by the difference between these two vectors. So therefore the circle touching any of these points implies that the difference between these two vectors is now a valid reciprocal lattice vector, and therefore a circle touching any of these points satisfies this equation with this being true. So it satisfies the equation that s by lambda minus s naught by lambda equals HHKL. This equation is satisfied, I have plotted this in a 2-dimensional sense. So in this 2-dimensional figure this equation is satisfied whenever this circle touches any of these points. As you can see clearly there are several points here which are not being touched by the circle, therefore with respect to those points diffraction is not going to occur, that is number 1. And number 2, there are several regions of the circle which are not touching any point, okay. So therefore if you looked for diffraction in this direction, for example, I will just draw a dotted line here, okay. So this is another s by lambda direction, again the magnitude is still 1 by lambda, but it is in a different direction, so a different s, okay. So if you want to call this S1, that is S2 direction. In this direction diffraction will not be visible for us, because in this direction there is no, the circle is not touching a valid reciprocal lattice point, it is simply touching a region in reciprocal space where there is no valid reciprocal lattice point. Therefore, at this point the difference between these two does not result in a valid reciprocal lattice vector. Okay, so that is the significance of this equation when it is actually drawn in a reciprocal space notation. When reciprocal space notation is used and it is actually drawn here, this is what you see. This is okay, so this is what it is. The figure I have drawn here is in 2 dimensions. So in fact when you see here we have a B1, B2 and B3. So actually this information can also be drawn in 3 dimensions. Okay, so when you draw it in 3 dimensions, what you see as a circle in 2 dimensions is actually a sphere in 3 dimensions, because this vector is fixed, OA is fixed, this vector OB can actually go in all directions around it, starting from the this vector AB with A as a center, this B can go in any direction around it. So what you will see then therefore is a sphere, only the length AB is fixed, length AB is 1 by lambda, so that is fixed, there is no change in that, but the direction of AB is free, we can put it in any direction that we wish. In fact we can put it in all directions. When you put it in all directions or you project it, I mean allow it to go to all directions, all possible directions, what you will get is a sphere. You simply have one end fixed and you have the other end able to rotate in any possible direction you wish, you will get a sphere. So what you see as a circle in 2 dimensions is actually a sphere, and what I have just shown you a 2 dimensional set of points because I only used B1 and B2. So the reciprocal lattice itself will exist in 3 dimensions for a real material, it will exist in 3 dimensions because you will have B3 also. So in the same way you can plot B1, B2, just the way I plotted B1, B2 you can additionally put B3 points here and behind the board. So you will get a 3 dimensional set of points corresponding to valid reciprocal lattice points, and you will have a 3 dimensional sphere. Any place the surface of the sphere touches one of those reciprocal points, you have a valid condition for diffraction. Okay, this construction is credited to Ewald and is therefore called the Ewald sphere. This way of indicating to us when diffraction will occur is credited to Ewald and he is called the Ewald sphere. It is also called the sphere of reflection. Okay. So this is a very important construct, it is a construct in reciprocal space. There is a sphere corresponding to which carries all the information related to the beam that we are using or the waves that are present that we are considering, and it and therefore it encapsulates that information, and the lattice itself encapsulates the information of the material, of the periodicity of the material. So this is what we have seen. Okay, so we find now we have progressed quite a bit, we understand that the interaction between waves and a periodic lattice can result in diffraction, that was something you were already aware of. This is described to us using Bragg notation, that again you were aware of, we briefly looked at it in the last class. It is also something that we can describe in reciprocal lattice notation. Okay, and independently we have also defined reciprocal lattice, and we understand that we defined it by saying that for any given lattice we can define a reciprocal lattice given certain relationships holding true. On the basis of that relationships we can generate the reciprocal lattice. Now so we have come this far. What I want to highlight now is that we have on this diagram I think we have a good feel for the fact that there is a wave arriving in a particular direction which we are simply designating or denoting by 1 by lambda, but the same direction, correct direction, and we are looking for the diffracted beam in some direction which we are designating by S, and 1 by lambda is the magnitude. So that part I think we have a good feel for. What I would like to improve our feel for is the reciprocal lattice itself. Okay, so in the next few minutes through the rest of this class we will look at the reciprocal lattice and understand certain aspects of it so that we have a better feel for this whole picture, because intuitively we have a better feel for real space. To have a feel for reciprocal space is not that intuitive for us, so that is what we will look at. Okay. Now the point so far we have simply said A1, A2 and A3 are real lattice vectors, which then give us a reciprocal lattice set of reciprocal lattice vectors which are B1, B2 and B3. based on the relationship that B1 is A2 cross A3 divided by the volume which is simply A1 dot A2 cross A3. Okay, volume of when you have 3 vectors and if you want to calculate the volume of that region described by the 3 vectors, this is the formula for it, A1 dot it is a triple product A1 dot A2 cross A3. So you will get the volume. So this is all we have done, we just stated it like this, and on that basis we created the reciprocal lattice, we kept that as a independent entity, and then we have looked at diffraction. So these are all, to some degree these are all independent pieces of information. Possibly for another class we will still continue to look at independent pieces of information with, or at least information where the links between them seem a little loose at this moment, but it will all tie in together in a class or so. So therefore you have to be a little patient and proceed on that basis. Now what I want to draw your attention to is that right now it is simply A1, A2, A3, B1, B2, B3. Okay, so it seems like something that is detached from our standard discussion. In real materials what do we have? We have crystal structures, we have, you know, we can say it is simple cubic, we can say it is face centered cubic, we can say it is body centered cubic and so on. So when you take a real sample, we want to, all the discussion we are doing, we are trying to do so that we can carry out, so that we can understand something about a real material, okay, a real material and what its properties are, why its properties are whatever they are, and how can we understand that these are the reasons why the property is what it is. So we have a real material may have one of these, I mean it may have several structures, we just illustratively we look at say simple cubic, face centered cubic and body centered cubic. So that is what is being described by A1, A2 and A3. When you say something is simple cubic, correspondingly there will be an A1, A2, A3. If you say it is FCC or face centered cubic, it will have an A1, A2, A3, and BCC will similarly have a corresponding A1, A2, A3. When you take that real material and you want to consider, you know, what is happening with respect to diffraction in it, how is that real material interacting with some radiation, what is the result of that interaction and so on. We have just seen that we can plot all this information in reciprocal space and then we get this sphere, and with respect to that we can say a lot of things. Therefore we have to do 2 things. First is that the material itself, okay, we have to depict this material in reciprocal space. That is the first thing we have to do, and that is that simply means that for the A1, A2 and A3 that we have here, we have to get B1, B2 and B3. Once we get B1, B2, B3, the way I just currently in our previous plot here where we looked at here, we looked at plotting B1, B2, B3, we can do that, we can plot B1, B2, B3, and of course once you know the wavelength of the radiation and which direction the radiation is coming in, we can incorporate that information in here and we have all the information we want, fine. So we have to get here. So therefore we need to have a better understanding or better feel for how A1, A2, A3 relate to B1, B2, B3. The equation is given here, that is fine, the equation is definitely given here, and in fact this is the equation we will use, but we will look at these 3 specific cases of simple cubic, face centered cubic and body centered cubic and see what does this equation do. I mean, is there something that we can physically understand about what this equation has done with respect to these 3 structures and what is the result of it. In other words, given those 3 structures, if you get B1, B2, B3, what will we really have? So let us start with simple cubic. So a good way of describing it is A1 is simply AX, okay, so we will say A in the X direction, X cap, A2 is A Y cap and A3 is A Z cap, where these are unit vectors in those directions X, Y and Z, okay. Now we would like to get B1, B2 and B3. So we have taken a simple cubic lattice, so the magnitude of the vectors A1, A2 and A3 are the same, A and A, that is why it is simple cubic, okay, it is cube, it is a cube, so all sides are A. So in all 3 directions we have the same magnitude A, only the direction differs, it is in X direction, Y direction or Z direction, that is all we have, fine. So given this lattice, what is the reciprocal lattice that we will get? So first thing we will need to do is we need to calculate this bottom part, which is the volume of this reciprocal lattice. So we will do that. We need A1 dot A2 cross A3. What is A2 cross A3? A2 I mean the magnitude simply is A square, right, A square A2 cross A3 A square, it is y cross z, y cross z is x, x y z, if you have 3 coordinate system y cross z is x. So therefore this is simply A1 is still the same, A x cap dot A2 cross A3 we will pull out the 2 A's, so we get A square, and y cross z is x. So this is simply A cube, which of course we know for a simple cube if you have a side A the volume is A cube. So that is what it is, except that we find that when you use the vectorial notation we are getting an answer that is consistent with what we already know, A cube we have. So now we need to simply calculate B1, B2 and B3. B1 we will put it here, B1 is A2 cross A3 which we already just calculated as A square x divided by this volume A1 dot A2 cross A3 which is A cube. Okay, so therefore P1 equals 1 by A x cap. Okay, so in other words B1 the reciprocal lattice vector has the dimension of 1 by A and the direction is still x, and then similarly B2, so B1 equals 1 by A into x cap, B2 if you did the same analysis you will have A3 cross A1, A3 cross A1 is z cross x which is y, so it will become y cap 1 by A, and B3 will become z cap 1 by A. So what do we have here? We have the directions are still x, y and z, unit vectors are still in the x, y and z directions, magnitudes have become 1 by A, 1 by A, 1 by A, alright. So if you take a simple cube of side A, its representation in reciprocal space will continue to be a simple cube because the dimensions, the magnitudes are the same, right, it is 1 by A, 1 by A, 1 by A, the magnitude is still the same. So we have 3 mutually perpendicular directions x, y and z, 3 mutually perpendicular directions along which we are travelling the same distance 1 by A, 1 by A, 1 by A. So we continue to have a cube. So a simple cube in real space remains a simple cube in reciprocal space. It is only that the dimension of the cube has changed, where the dimension of the cube was it was a cube of side A, it is now a cube of side 1 by A. So therefore if you were to plot, if you have a real material which has a simple cubic structure, okay, a simple cubic structure will then consist of points which are cubically arrayed. So you will have an origin, an atom at A, another atom at A there, another atom at A there, and that is the way you will build the simple cubic structure. This same material, if you want to understand what is happening with respect to how it is interacting with waves, especially electromagnetic waves, we will have to first represent this in reciprocal space. Its representation in reciprocal space will continue to be a simple cube, except that the dimensions will now be 1 by A. So you will now make 1 by A, 1 by A and 1 by A in 3 directions, and you will build the lattice. Now that is a reciprocal lattice of the original material you were discussing, you are interested in. Okay, so whatever is the original material, you have now created its reciprocal lattice. It is now a simple cube of side 1 by A. So that is what that will form the set of points here, and whatever wave we are talking of, that will independently form the sphere. So the sphere is independently formed based on the radiation you have chosen. The set of points that are there, which are reciprocal lattice points, are based on the material you have chosen, which happen to be simple cubic. Therefore the reciprocal lattice also happen to be simple cubic, and then you see the interaction based on this relationship, you know when diffraction will occur or when it will not occur. Okay, so this is with respect to simple cube. We will also look at face centered cubic and body centered cubic. So we will start with face centered cubic. Here by convention A1 is designated as A by 2 y plus z, A2 A by 2 z plus x and A3 A by 2 x plus y. Initially immediately maybe these vectors do not immediately convey to you the sense of a face centered cubic structure that you are more familiar with, but actually if you take a moment you realize that in fact it is. What we have plotted is these are vectors which connect the origin of that face centered cubic structure to the 3 face centers. That is what these vectors are. This vector goes to a face center that is halfway between if you travel half the distance along y axis and half the distance along the x axis, half a unit vector along y axis and half a unit vector along x axis, then you find that you have reached a face centered location. So the origin connecting it to the 3 face centers, so that is what we have, 3 face centers, that then forms the unit cell that we are interested in, and on that basis you can build the rest of it. Okay, so therefore this is fine. These are the unit vectors that we would select in real space corresponding to a face centered cubic structure. Given this, what is the reciprocal lattice we will get? B1, B2, B3. Okay, I will we will do the calculation of B1, B2, B3 and then we will see what it comes to. So again we want the A1 dot A2 cross A3, that is the volume that we want. Similar, so B1 is still the same thing, A2 cross A3 by A1 dot A2 cross A3. Okay, so what do we have here? We will just look at this A2 cross A3. So A2 cross A3, this is what we have to do. So of course these two will get multiplied, so we will have A square by 4 and then we have to write this down here. So we will do that. We will write x cap, y cap, z cap. Z plus x would mean we will write it as 1 0 1 and then x plus y we will write as 1 1 0. So we can evaluate this. This is a square by 4 times x cap into 0 minus 1, all right, plus y cap into I am sorry, minus y cap. This is just a standard expansion of what we have here, minus y cap 0 minus 1 0 minus 1 plus z cap into 1 minus 0. Okay, so this is simply a square by 4 into minus x cap plus y cap plus z cap. This is simply the cross product A2 cross A3. Okay, now we will do a dot product with so this we already have the numerator actually, so we already got the numerator. The denominator is simply this same A2 cross A3 dot A1, so the denominator is going to be dot product of this and A1 here. So A1 dot A2 cross A3, so this is what we have here is simply A2 cross A3. Okay, so that is what we already have. A1 dot A2 cross A3 is this dot product. So this is this will become A cube by 8, right, and then we have y plus z. Okay, so y plus z, so it is basically 0 1 1 and we have minus 1 1 1. So y times y will become 1 and z times z will become 1 and the dot product. So therefore this is a cube by 4. So this a cube by 4 is the volume that we have for this unit cell, and this is the unit vector, I mean this is the vector A2 cross A3. So if you divide A2 cross A3 by this volume here, you are simply dividing this entire term here by a cube by 4. So therefore B1 will be actually 1 by a, because that if you divide by a cube by 4, the 4 and 4 will get cancelled, you will have a square by a cube which is 1 by a times minus x cap plus y cap plus z cap. So this is B1. Okay. Similarly, if you do the calculation by symmetry, you will find that B1 gets you a minus x plus y plus z, B2 will get you a minus y plus x plus z, and a B3 will get you minus z plus x plus y. Okay. So for example, we will just write it here, B2 will simply be the same 1 by a plus x minus y plus z, and B3 will be plus x plus y minus z. Okay. So we once again find that the dimension is 1 by a, so that part is still the same. So we have, in that sense we understand that in terms of magnitude we have gone from a scale of length to 1 by length, so that is consistent with our feel for what reciprocal space is. So 1 by a we have gone, and these are the vector directions, minus x plus y plus z, x minus y plus z, and x plus y minus z. In fact, if you actually plot this up, if you make a plot of this, you will find that it is the same as a body centered cube, wherein these are vectors going from the origin to the 3 body centers. Okay, so to 3 neighboring body centers is where it is headed. So that is how we are getting the 3 body centers, and then you can build your structure around it. So in other words, I mean right now you have to just take my word for it, but if you just plot it, you will find it. If it's x plus y, you are going along x direction plus y direction, so you are getting to a point minus z, so you are going down, so you are getting to one body center in that location. If you went only x plus y, you would get to the face center, right, x plus y and with some constant. So in fact a by 2 x plus y would get us to the face center, which is what this is. A by 2 x plus y gets us to the face center, a by 2 z plus x gets us to the next face center, a by 2 y plus z gets us to a third face center. So these are face centers, right. So along the x direction you can go the full a, instead you are going only half the a, and another y direction also you can go the full a, you are going only half the a. So in between this x half a and the other y half a, you come to the face center. So that is why these are face center locations. This minus x plus y plus z would simply mean you are coming halfway and then you are going down also one more, and that therefore you are reaching a body center. So these 3 therefore represent body centers, although the scaling factor is different, but you have now gone to the reciprocal space, so it is 1 by a at the moment. So we will have to just let us not worry about the scaling factor, but the general layout of those 3 points is as though you are reaching out to 3 body centers. Okay. So what we find is, if you take a face center cubic structure in real space, in other words you take a material, okay, so you take silver, you take copper or whatever, some face centered cubic material, and then you you represent this material's crystal lattice in reciprocal space, you will actually be representing it in the form of a body center. Okay. So that is something you have to understand. A simple cubic structure represented in real space being represented in reciprocal space continues to remain a simple cubic structure, whereas a face centered cubic structure, when you try and represent it in reciprocal space, it is being represented as a body centered cubic lattice. Okay. So this is an important thing we have to note. The last thing we will do is for the BCC structure itself. So we are starting with the BCC structure. Okay. Here we started with an FCC structure and we have arrived at a BCC structure. So this, our result here is BCC. Okay. It is in reciprocal space, that is why we have 1 by a, so that I just mentioned it, let us not worry about 1 by a. In BCC in fact we would have A1 is a by 2 minus x plus y plus z, A2 is a by 2 x minus y plus z, and A3 is a by 2 x plus y plus z, so I am sorry, minus z. As I mentioned, this is very clearly going from the origin to the 3 body centered, the body centers. This is a by 2, which gives you the dimension that you are only travelling half the distance of that valid reciprocal lattice length, I mean I am sorry, valid lattice length, I am sorry. So this is a lattice length or lattice vector A is A, and so you are travelling A by 2, and then you are travelling halfway between, so you are travelling in the y and z directions to half that length, and then down the x direction half the length. That will get you to a body centered location. Similarly, this will get you to a body centered location, this will get you to a body centered location. So these are 3 vectors that go from the origin to the 3 body centers, fine. So therefore this is body centered cubic structure, this is representation of body centered cubic structure. Directly you can see that this looks very similar to where we finished off here, exactly the same vectors you see here, only difference is the scaling factor. So the scaling factor we need not worry about, but it is the geometry that we are interested in here. The geometry that was face centered cubic as we started out with, when we converted that to a reciprocal lattice notation, it became a body centered cubic. Please keep in mind, as I mentioned right at the beginning, this is only for our convenience, okay, in the sense this is just a notation we use to serve some purpose. The material is still face centered cubic, nothing has happened to the material. It is not that the material suddenly became body centered cubic, material still remains face centered cubic. When we want to understand how it is interacting with radiation, we want to use the reciprocal lattice notation to see how it is interacting with radiation. We see what does this structure, how is this structure represented in reciprocal space. It is simply a representation of the face centered cubic structure in reciprocal space, that is all. The material still remains FCC, that is the thing you have to remember. We will do the same thing now for BCC. We will do A2 cross A3, so we have to do B1 is A2 cross A3 by A1 dot A2 cross A3. What is A2 cross A3? We have to take a cross product of these two, that is again A2 by A by 2 will become A square by 4, and we can write x cap, y cap, z cap, and this is plus 1 minus 1 plus 1, and this is plus 1 plus 1 minus 1, 1 1 minus 1. We expand this, what do we get? We get A square by 4 x cap, this will become plus 1 minus 1 minus y cap minus 1 minus 1 plus z cap 1 plus 1. So this is therefore A2 cross A3 equals A square by 4, this becomes 0, so this term goes away, this becomes minus 2 times minus 1 becomes plus 2, 2y plus 2z. So it is basically A square by 2 into y plus z. That is the cross product A2 cross A3, and the denominator is A1 dot A2 cross A3 okay. So that is simply the dot product of this A1 that we have here and this A2 cross A3 that we have already seen here. Dot product, there is an x component here, there is no x component there, so that goes away, so this is irrelevant to us. There is a y component and a z component, a y component and a z component. So y dot y will be 1 plus 1, z dot z will be plus 1, so we simply will get plus 2, and a by 2 into a square by 2 will become a cube by 3, a cube by 4. So this is a cube by 4 times plus 1 is 2, so this is a cube by 2. So therefore the denominator in this B1 is a cube by 2, the numerator is a square by 2 times y plus z. Therefore B1 is if you divide this by a cube by 2, you are simply going to get 1 by a y plus z. By symmetry you see 1 you only see y and z, so if you see 2 you will only see z and x, you will, if you take 3 you will only get x plus y. That is by symmetry. If you actually did it you will get it, because they are symmetric, there is nothing, there is no preference to any one of these axes, whatever result you see everything will symmetrically change for the other two. You can do the calculation, you can simply carry out for B2 and B3 just the way we have described the way we have except correspondingly these vectors will change. If you select B2, this will be A3 cross A1, this denominator will remain the same, denominator will still come to the same thing, it does not really matter which way you do it, you will always get A cubed by 2, right. So, so the denominator is not going to change in any significant manner, it is going to remain the same, in fact it is not going to change, it is going to remain the same, only the numerator will change. For B2 you have to look at A3 cross A1, and for B3 you have to look at A1 cross A2. So if you do this you will get the answers. You will find B2 is 1 by A x plus z, and B3 is 1 by A x plus y. This is what you will get. If you look at what we have got here, if you compare with something that we started out just a few minutes ago, we will have the FCC structure we defined as this: a by 2 y plus z, a by 2 z plus x, a by 2 x plus y. These three directions, the magnitude is something else, let us not worry about the magnitude, look at the three directions that we have here. We have the same dimension in three directions, and those three directions are listed here. If you go to our result just now, we have the same directions here: y plus z, x plus z, x plus y. Those directions are the same, and it's one magnitude regardless of what the magnitude is. In this case the magnitude is 1 by a, the same magnitude in those same three directions. So this is a representation of BCC, I am sorry, this is a representation of FCC. Okay. So what have we reached, what have we done here today? We have really looked at few things. First of all, we understand that we can represent diffraction as a process. Diffraction is simply the interaction of waves with electromagnetic waves with a periodic crystal structure. So that is a concept, right. We can represent it in real space and write an equation which tells us under what conditions diffraction is occurring, that is Bragg's law. You can represent the same information in reciprocal space and see under what conditions diffraction is occurring, that is the Ewald sphere construction. So either way it is the same information, it is the same material, it is just being represented either in real space or in reciprocal space. That is a piece of information we understand. Now we also want to understand that if you are given a real material and it has a certain crystal structure, what will how will you represent that crystal structure in reciprocal space, so that you can now see the diffraction process in reciprocal space. We find from the discussion that we have had that if our original material happens to be a simple cubic material, structure happens to be simple cubic, then its reciprocal lattice, the B1, B2 and B3 that we calculate, the layout of those reciprocal lattice vectors is still simple cubic in geometry. It is the same magnitude in x direction plus y direction plus z direction. So it is one single magnitude that happens to be in the x direction, y direction or z direction in three mutually perpendicular directions. So therefore the layout of this information of a simple cubic material in reciprocal space continues to be simple cubic, only the magnitude has changed because we have now gone to reciprocal space. If we start with the face centered cubic material and we take the three characteristic vectors that represent a face centered cubic material, and we run through the calculations corresponding to reciprocal space, we find that the reciprocal lattice that is generated that corresponds to a real material having an FCC structure happens to have the vectors which are similar to the vectors of a body centered cubic structure. So therefore if you have a sample that is face centered cubic, you will have to plot the points in reciprocal space the manner you would do for a body centered cubic material. Okay, we are only talking of geometry. Geometry in real space is face centered cubic. This same material when represented in reciprocal space will have to have a geometry that is similar to that of a body centered cubic material. Okay. So the layout of the points, when you make these points in this figure here, when you lay out those points of that body of the face centered cubic real material has face centered cubic, when you plot this reciprocal lattice points here B1, B2 and B3, when you plot them, those B1, B2, B3 will have a layout which will look very similar to body centered cubic, will be identical to a body centered cubic layout. Okay. So that is the thing. Third thing we did the other structure which is body centered cubic here. We took the characteristic vectors that represent body centered cubic atoms, we looked what would happen if we just went through the standard, we are enforcing the rules of reciprocal space, reciprocal lattice. We said that B1, B2, B3 have this relationship to A1, A2 and A3. If we enforce those relationships, we find that the vectors that result are these vectors which have a layout that is identical to face centered cubic. So if you have a real material which is body centered cubic, okay, so you have a real material that is body centered cubic and you want to represent it in reciprocal space so that you can see its interaction with waves, then its representation in reciprocal space will have some dimension 1 by a, and the layout of those vectors will be identical to face centered cubic material, okay. So that is what it is. So to finish this class, I want to just highlight a few points that I made throughout this class. The first is that the reciprocal lattice notation which is represented in the form of this Ewald sphere tells us how the matter is interacting with the radiation and therefore or waves in this case, and tells us when diffraction will occur and when diffraction will not occur. It gives us a nice elegant geometrical look at how when diffraction will occur, when it will not occur, okay. So that is one information, and we also we have also seen in this class that when you do this transformation from real space to reciprocal space, some structure that has a certain geometrical layout in real space may have a different geometrical layout in reciprocal space. In the case of simple cubic, it happens to have the same layout. In the case of FCC and BCC, it has a different layout in reciprocal space. The information is still the original materials information, it is only the representation in reciprocal space that has a certain style, certain layout, and it so happens by chance that when you take face centered cubic material, its representation in reciprocal space happens to be that of a body centered cube, and if you take a body centered cubic material, its representation in reciprocal space happens to be a face centered cube. So these are all independent pieces of information that we will keep in mind, okay. Later on we will see that so when we go from real space to reciprocal space, we understand that structures can change, so it is not something that we should feel afraid of or confused about. We also understand how we can figure out what has happened to the structure, those are the calculations we have done, and we also understand that having come to reciprocal space, we have the understanding of how to figure out what is happening with respect to interaction of waves with that structure, okay. So these are all independent pieces of information. Finally, when we go to our next classes, next few classes, when we look at electron waves and how they interact with matter, it is all these concepts that will be pulled together, okay. And at that stage, again, as and when necessary, I will highlight those salient points which will help us relate to this material. I will only finish off with one other comment, which is basically that in these last couple of classes and maybe the next class or two, we are talking of some independent pieces of information and then looking at them in great detail. So please feel free to review this information when you come to one of the later classes when we pull this information together, so that you can understand in case you are having some difficulty following at that stage in terms of how they are coming together. Come back and check one of these classes, see what this information is as an independent entity. You will be able to relate it to our discussion later much better, okay. So with this we will halt for today. Thank you.